So we've been studying up to this time resistors, and we've been really hitting resistors pretty hard. What they are, resistivity, resistors in series, resistors in parallel, resistors in series and parallel. We've been going over a lot of those formulas. And we're not going to be studying capacitors or inductors to any great degree. And certainly not to the degree that we've been studying for resistors. And the reason is it's not that there's anything magical about capacitors, but the equations for capacitors are not like resistors. You can connect resistors in series and parallel and a combination of the two and use algebra, simple algebra, to come up with some answers. Total resistance, you can use Ohm's law, you know, all the power equations. But with a capacitor and with an inductor, when we get into inductors, the equations are a little bit more complex. These are energy storage devices, so they take energy from the circuit and then they give it back. They take energy when the alternating current is greater than the when the capacitor is uncharged, they take energy and charge up, and then when the AC cycle is going down, they discharge. So it's kind of like a miniature battery. And in order to explain mathematically what's going on, you really need a good level of calculus, and you get into a branch of mathematics called differential equations. And if you don't know, if you don't have a good background in that kind of stuff, you're just going to be totally lost. And this is a basic course, and so there's just no reason to get into capacitors in any great detail. So the question is, what is a capacitor? What exactly is it? Well, we all know that number one, it is one of the three basic fundamental electrical components, passive electrical components. We have resistors, we have capacitors, and then later on we're going to be studying inductors. And of course, I might have said this before, I'm not sure, but the reason you only have three, why is it you only have three in all of electronics and electricity? And the reason is, it goes back to the fundamentals of electromagnetic field theory. You can only store energy in an electrical circuit three ways. One is an electric field, that's a capacitor. One is a magnetic field, we're going to be getting into that later, that's through an inductor. And the third way is electromagnetic energy. Now, that's resistors. You know, resistors don't really store energy. They do for just a short period of time, but they as soon as power goes through a resistor, the resistor heats up and gives off electromagnetic radiation in the form of heat. So it's not really a storage device, but it does operate on the principle of electromagnetic energy. So you have electrical energy, magnetic fields, electrical fields, magnetic fields, electromagnetic, three basic devices. Well, we know that current is nothing more than the flow of electrons through a wire. And so in a capacitor, what we do is in order to store that charge, if you want all electrons having charge on them, a capacitor then is nothing more than a device that takes advantage of that ability of that charge to store energy in the form of plates. So a capacitor is nothing more than a device that consists of two metal plates, like so. These are very basic diagrams. So that if you connect this to a battery, and you have a switch in here. As soon as you throw that switch, you're going to have current flowing from here, from the battery, onto this plate. So you get a bunch of electrons like this, charging up that plate. At the same time, those electrons are going to be flowing from that other plate back to the battery. And so this plate here, this piece of metal here, is going to have a positive charge. And by definition, whenever you have a charge accumulation, in this case on two plates, by definition, you have an electrical field that is being generated, and by definition, that electrical field is in the direction from positive to negative. Okay? So here we have electrons. The field, the direction of the field is opposite the flow of current. And when you connect, when that switch is thrown and that current starts to flow, the electrons will just start flowing onto that plate. And until the voltage across that plate is equal to the source voltage. So as the electrons start flowing onto that plate, at first it's pretty easy. There's really no opposition to the flow of electrons onto that plate. As the electrons begin to pile up, however, the electrons that are already on the plate are going to start repelling the electrons that want to get onto the plate. So because like charges repel. So as time goes on, the current flow, when you throw that switch, it's going to be really high. It's going to hit a maximum value the instant that you throw that switch. So here's the current, here's time, here's the current. So that current, as soon as that switch is thrown, is going to jump to a maximum value. The value is going to be determined by the amount of resistance in the circuit. And then over time, it's going to start dropping like so. As the electrons start piling up on here and repelling the electrons that are coming onto the plate. By the same token, over on this plate, you have, as soon as that switch is thrown, the electrons are going to be flowing from that plate onto that wire. What happens is now you have a positive charge that starts to accumulate on this particular plate. You have a positive charge. And so the positive charge is going to keep the electrons from flowing. It's going to start pulling the electrons back the other way. As the current, at first on this side, the current will be a maximum, and as the positive ions build up and the charge increases, they're actually going to pull the electrons back onto the plate. And so there, again, you're going to have this kind of a relationship. The current's going to be the same everywhere, no matter what. And so the end result is that when, at some point, the charge on this capacitor is going to pretty much equal the battery voltage. And when that happens, we say the capacitor is fully charged. Okay? It's just, in principle, it seems it's a fairly simple thing. Now capacitors can be constructed in a variety of shapes, a variety of sizes. I think there's a couple in the drawer out here. Okay, so capacitors come in a variety of shapes and sizes. And I don't even know that those things work or still operational. But if you, so in this parts kit that I have, and I think in your analog kit, you've got these little guys which are really, really small. Here's a sort of a one that's a little bit bigger, but you can see that the shape sort of gives you the impression that that each lead is connected to like something, you know, a piece of metal. And in fact, you can see the impression of the wire if you look at the capacitor. And then it's literally spot welded to the plate. So inside that capacitor there you have two round plates, like so, and the wire comes out, and you have another one behind it, like so, and that creates the shape. Those are just two real small plates that store the charge. Here's a capacitor there, a little bit different shape, 7.5 microfarads, and I want to go over the ranges for you, the values. This guy here is 31,000 microfarads. Wow. And this is 60,000 microfarads. So that's 60 millifarads, 0.6 farads. So they're massive, they're huge capacitors, and yet the value is of the capacitance is relatively small. Okay, so let's just go over some numbers here. You have current flowing in this direction. Current is, we learned earlier, it's charge divided by time, coulombs per second. We have current, the same amount of current flowing here. And while the current is flowing onto this plate and off of this plate, you have voltage being built up between the two, and there's a relationship between voltage, current, and capacitance. We'll go over what capacitance is, and it is this. Q equals CV, where this is the charge in coulombs. This is the voltage, and this is the capacitance, which is measured in farads. Isn't there a shopping club called QVC? Did you ever hear of that, QVC? Mm-hmm. So if you ever have trouble in the book, this is the formula in the book, but if you ever have any doubt in your mind about the formula for capacitance, voltage, and charge, I always write it that way. It's like the shopping club on TV. So I start out with this, QVC, and then I just put my equal sign there. That's the same formula. In the book, though, it's Q equals C times V. So capacitance is nothing more than a measure of the amount of charge versus the voltage. And capacitance, by definition, is the ability of a device to store energy in the form of an electrical field. Capacitance is nothing more than the ability or a measure of a device or a system to store energy in the form of an electrical field. Everything has capacitance. If you have a straight wire between point A and point B, let's say a transmission line outside, high voltage line, there is a certain amount of capacitance between that line and the ground. As a matter of fact, I mean, how many of us have gone, and of course when you, we're going to get into all the capacitors in AC circuits after the spring break, but when you have capacitors in an alternating circuit, alternating current circuit, the charge on that capacitor, it just goes back and forth because of the AC wave. And so in a transmission line carrying alternating current, high voltage line, they act like antennas. And they just radiate all kinds of energy. And you know that whenever, if you've ever been on a highway and you've driven underneath a transmission line with your radio on, and your radio just goes nuts until you get away from that transmission line. Well, that's what's going on. That transmission line is actually radiating energy, and part of that reason is the capacitance in the lines. So everything has capacitance. As soon as a wire starts carrying current, every device, resistors have capacitance. Believe it or not, when you start modeling resistors. It's just that for a basic class like this, we consider things ideal and we ignore the stray capacitance that exists in other elements. Okay? So the unit of capacitance is a farad. Now, so I just went over the sizes of these capacitors here. What's this guy here? So this is 7.5 microfarads. 7.5 times 10 to the minus 6 farads. That's not a big number, and yet how many of us would see a circuit with something like that in it? That's pretty big. And what I have here, I just brought this in just for the fun of it. This is one of my projects that I'll probably be dead before I even start this. But I had this crazy idea one day that I'd like to restore and rebuild an antique radio. I had a crazy idea. I started going through some yard sales, or started going to some yard sales, and I saw this thing on sale for $5, and I bought it.
Just like that?
Well, no, it has the tubes. Do you know what vacuum tubes are?
Yeah.
You guys know? Okay. So it had the tubes with it, and it had the wooden case. The wooden case is worthless. But I thought, hey, there's a project, $5. You know, I can rebuild that. And I don't know. I may. This is one of those. I may or may not get to this. But anyway, I brought it in because here is a capacitor that's a variable capacitor. You see, when I turn this. Look at these guys here. See that? You can see the plates. You see the plates moving?
Mm-hmm.
So the metal plates. Okay, you can play with this if you want to play with it. See the plates? So that is a variable capacitor, and that's how this radio tunes.
Looks like it's almost fixed.
Yeah, I mean, I didn't see any burnt components, so I think it might just be a vacuum tube. We'll see. I might get some inspiration this summer and fix that. I don't know. We'll see what happens. I don't even have a schematic for that. I would have no idea where to start without a schematic. But anyway, that's a variable capacitor. And so, like I said, there is a measure of there is a formula for calculating the value of capacitance based on the physical geometry of the plates. And it's in your book, it's this. Capacitance equals now, capacitance equals area divided by the distance between the plates. That's this guy here, distance. The area is the area of one plate, not two plates. So this is the area, one plate. And this is the Greek letter epsilon. And it actually represents two separate it actually has two separate components to it. So that epsilon is this guy here. And it has the name permittivity. It is called the permittivity constant. You can look in your book for the spelling. This epsilon 0 is known as the permittivity of free space, or the permittivity of a vacuum. Permittivity is literally the ability of a material to allow an electric field to pass through it. Think of it like as the resistance associated with an electrical field instead of current. Resistors oppose the flow of current. The permittivity is a measure of the resistance that a material offers to the flow of an electric field through it. I don't know how else to put it other than that. So this is the permittivity of free space, or a vacuum. And this is a permittivity of the actual constant of the actual material that's between the plates. So I'm showing a capacitor here with just air, but in these capacitors that I have that are in your analog kit, there's actually material between those plates. You don't want those plates to touch, because you'll get a short circuit if they do. And so, let's say this could be glass, could be a piece of plastic, could be wood, could be anything really that doesn't conduct. But that would be, whatever that is, that would have a certain permittivity. And table 9-3 in your book has this is called the relative permittivity. Table 9-3 has the relative permittivity of a variety of materials. I think that's right, 9-3. So for my little radio here, it's just a variable capacitor, but there's nothing between the plates. So in that case, if I wanted to calculate the permittivity of that guy, this would be equal to 1. ER would be equal to 1. So the permittivity of air is so close to the permittivity of a vacuum, everybody just says it's 1. The permittivity of air is so close to 1, everybody just says it's 1. And the permittivity of free space it's measured in farads per meter, and it's on page 389. And it's 8.85 times 10 to the minus 12 farads per meter. I have no clue how they came up with that. Now, one thing you need to, if you ever come across this formula in your travels, even in guys who are in mechanical, you might have reason to look up capacitors, let's say for a capacitor start motor or something like that. This formula is only for a flat plate capacitor, only. Remember I said that capacitors, that everything has a capacitance associated with it? Well, the formula for the capacitance between a transmission line and ground is not this formula. I mean, I think of it, a transmission line is just a piece of wire, so there's really no area, no appreciable area that you can associate with it as you would for this kind of a capacitor. So the formulas are different. You have to start from basic physical principles, basic physics, and then once you start with some really basic equations in physics, you plug in the geometry of the system, in this case 2 flat plates, you end up with that formula. If you could have a capacitor like this with concentric plates, one inside the other, like 2 tubes, different formula. So if you wanted to calculate the capacitance for something like this, I'm assuming those plates they're probably stacked, so you have multiple, well, it might just be like a roll of metal, and you would have a different formula. So the only formula in the book is this guy right here. That's the only one. One more formula, and that is that, let's just say you have this this system right here. You throw the switch, electrons accumulate here, electrons leave that plate. This voltage is equal to this voltage. Everything's charged up. Current has stopped. What is the amount of energy that you can say is contained within that electric field between those plates? Well, the formula for that is this. The amount of energy in joules is 1/2 times the capacitance times the voltage squared. Again, that's a formula that's derived from basic physical principles. Okay? So this is measured in joules. Here's farads. And this is voltage squared. So if you have a test, I give you the capacitance and the voltage, ask for the energy, you can use that formula to calculate it, or if I give you the energy and the voltage, what's the capacitance? Well, again, it's the same formula, different unknown. Who has questions? Now, in case you haven't figured this out, or maybe you have, when you connect capacitors have very limited usefulness in a DC circuit. I mean, the thing charges up. You connect the battery, throw the switch, the thing charges up, and then you can just disconnect the leads and it sits there. These capacitors, once they have a charge, they can hold that charge for a long period of time. And I'm talking about weeks, sometimes months. You got to be real careful when you're dealing with things with capacitors, devices that have capacitors. I had a 2x4 light fixture that burned out on me a couple of years ago, and I had replaced the lamps in it, and it still didn't work. So I thought, okay, the ballast is bad. And above inside the compartment, there's this device called a ballast, and it takes 120 volts from your house current and boosts it up to thousands of volts, and that's what lights the lamps. So I said, okay, I got a bad ballast. And I went to Lowe's, Home Depot, I don't remember where, bought another ballast, and this is like a couple of weeks. I hadn't operated this fixture for a couple of weeks. And I started to take the screws out that held the ballast in place, and I knew that these ballasts have big barrel capacitors. Not this big, but maybe something like that. You know, they're inside there. And I thought, okay, I'll just take this thing apart, replace the ballast, I'm good to go. And here, the leads for one pair of leads from that ballast, somehow I managed to short them. I like to take things apart, so I think I took the cover off the ballast. I'm playing around with it. And whammo, this thing, I just had to, it gave, you know, the shock, I discharged the capacitor, shorted it out, and I thought, man, I hadn't used this fixture in a couple weeks, and those things were still charged. So when you're working with capacitors, you really have to be careful, because you can get quite a jolt. All right? So but the usefulness of a capacitor in a DC circuit is limited. Like I said, they charge up, and at some point they discharge. But the real value of a capacitor is in an alternating circuit, and we'll get into that in a couple of weeks, where you have the electrons in an alternating circuit. You've got a voltage wave like this. Okay, so the current here in that part of the wave is going this way, and the current in this part of the wave, it's going that way. So no sooner does the capacitor get charged, or even partially charged, when the voltage reverses, electrons are starting to go this way, pile up on that plate, the voltage reverses, and all of a sudden they go this way. And so in effect, even though that's an open circuit, in effect, capacitors can very well, quite effectively, conduct current. And because of that, they have some interesting properties. Okay, so let's do a lab with some basic calculations, if I can find my labs. Oh, yep, I'm asking you to do something here and I didn't go over it. Let me just go over this very quickly. This has to do with, it's no big deal, it has to do with scientific notation. So the value of a farad, it is very rare that you deal with capacitors that are so huge. Maybe you'll see capacitors in a utility switchyard that are measured in farads. They're massive things. So most of the time we're dealing with capacitors that are microfarads, nanofarads. This little guy here is probably picofarads, 10 to the minus 12. I even have one that's a little bit smaller. So in your book, there's a table to convert pico to nano, micro to pico, you know, that kind of stuff. But it's really just scientific notation. So if I said to you, if I gave you a capacitor that was 47 microfarads, and I said express that as nanofarads, well, this guy here is 47 times 10 to the minus 6 farads, okay? That's microfarads. And so if I just move the decimal place, I went the wrong way. So if I just move the decimal place to the right, 47 1, 2, 3, I now have a capacitor that's 47,000 nanofarads, okay, or 10 to the minus 9. So there's actually a couple of pages in the text that have to do with expressing the value of a capacitor in different ways, from micro to nano, nano to pico, milli to micro, that kind of stuff. And like I said, it's just, if you know scientific notation and you know the prefixes, it's pretty simple, pretty straightforward. I think there is a table in there, though, that says when you go from micro to milli or whatever, you move the decimal places this way or that way. Sometimes you spend so much time trying to memorize those tables that it's not worth the effort. If you just remember your scientific notation and your exponents, you can do the same thing without any tables. Okay? Like everything else, the only way to really get a good grasp on this is to reinforce it by doing some problems. So let's do some problems. How are you feeling this week? Better? Are you still tired?
You watching the channel Superfly? Why is it? How much is it? With the oil? Oh. This way you won't be a solution. That's so stupid. That's what I'm thinking. Same. This is all we can do, isn't it? It's already in the pocket, so it's. Yeah, but I mean, I like to use that.
you have a capacitance meter on here?
Yeah, fine. What did I do? I went 12. That was my fault. Any others? That was it. Thank you.
You do? You have 4 of them? Yeah, those are your, 1, 2, 3, 4, those are your .47. So there's there. I thought this was your 40. No.
I'll check contact, please.
Oh. Did you find it? Wow.